And the next speaker is Ilya Zelkovich. So Ilya, are you ready?
Yep.
Ilya will present a talk, magnetic field tunnel density waves in a layer altermagnets, chromium selenide. So thank you, please, the floor is yours.
Okay, well, I'd like to thank the organizers for inviting me to speak at the workshop today. So I'm Ilya Zelkovich. I come from Boston College, and today I'll tell you a little bit about our work using scanning tunneling microscopy and spectroscopy to study a new layered altermagnet, which is this cobalt intercalated niobium diselenide. So here's a brief outline of my talk today. I'll start with a quick introduction to this new layered altermagnet candidate, cobalt intercalated niobium diselenide, which is going to be the focus of my talk today. I will introduce the technique that we use, which is STM and spin polarized STM as well. And then I will jump into three different sets of experiments that we perform in this system. The first one involving imaging charge and spin modulations on the surface of this material. The second one involves magnetic field measurements and what is the tunable nature of modulations and electronic density of states of this material using magnetic field. And at the very last, I'll talk about some of our unpublished data that involve imaging, nanoscaling homogeneity, and domain formation in the system. So we already heard a lot of focus on altermagnets and introduction to altermagnets here. So I won't belabor the same point too much, but I just want to briefly mention that altermagnets come with some of the same properties from either ferromagnets or antiferromagnets. So they have this spin split band structure, but zero net magnetization. So in essence, it was predicted first from theory that various unusual phenomena can emerge, such as anomalous Hall effects, spin polarized currents, and so on. And with this idea in mind, especially in the past few years, there was increasingly growing list of altermagnets that people are pursuing. Most of the focus so far has been on manganese telluride, ruthenium oxide, but I believe the list is growing by the day. So today I'll tell you about a different altermagnet. So it's intercalated niobium diselenide. One of the nice features about this system, it is a layered system. So niobium diselenide is kind of the starting building block. Pristine niobium diselenide is a material where you have these niobium atoms sandwiched between selenium layers, so to create these green prisms that you see. And then without intercalation, so pristine niobium diselenide is non-magnetic. It is a superconductor with a TC below 7 Kelvin or so, and it has a 3x3 charge density wave phase. Now, when you intercalate cobalts with this very particular content, such that you create this order superlattice between the layers, so cobalt actually goes in this van der Waals gap between the niobium diselenide slabs, it does become an A-type antiferromagnet. And from theory, DFT calculation, this is a Fermi surface at one particular KZ, where you can see this spin split band. So blue and red corresponds to different spins associated with these bands. So first, it was theoretically predicted that this system might be an altermagnet, and then the natural tool to use to investigate this is ARPETS. And I highlight two works here from two different groups on this system that have investigated whether there is some kind of spin splitting of the bands. So if you focus on the image on the left here, and then there's seemingly one band here, and then we take line cuts along these black lines, what you will see if you do spin resolved ARPET is that the spin up and spin down curves are slightly different. So now if you take the equivalent line cuts at an inequivalent endpoint, what you will see is also spin splitting of these bands. So red and the blue curves are slightly different, but the red and the blue are reversed compared to this endpoint. So this is exactly what you would expect from, I guess, theoretical calculations of this band structure. On the right, you can see the Fermi surface. So now I'm showing KX, KY plot here. And then it might be a little difficult to see on the screen, but this flower petal that corresponds to spin splitting of the bands, you can kind of resolve this in the ARPES measurements as well. So there's overall a good agreement between this large-scale electronic band structure and DFT calculations of the system in the ultramagnetic state. Another interesting thing about this system, unlike some of the other ultramagnets that are studied, is it actually has two different transitions. So the first one occurs around 150 Kelvin, and the second one occurs around 50 or so Kelvin. And the higher temperature transition is likely due to this A-type antiferromagnetic ordering. So there spins up, down, up as you go along the C-axis. But this lower temperature transition that you can see in this susceptibility measurements, there's a little kink here. Also, you can see it in these optical reflectivity measurements right there. That occurs anywhere between 30 to 50 Kelvin, depending maybe on the sample. It's still a little bit of a mystery. So it seems like there's something more going on compared to just a conventional A-type AFM ordering. So the aim of our experiments, and what I'll tell you in my talk, is to investigate how this system cools down into this ultramagnetic state and see what's going on at the atomic length scales. So first, let me, show you briefly the laboratory that we are using. So this is my MBE STM laboratory that I set up at Boston College. So we have both film synthesis facilities. So we have a couple of different MBE systems for the growth of thin films. It's not necessarily related to the talk today, since I'll be mainly talking about bulk single crystals, but I just wanted to highlight that my lab also grows various thin films of topological insulators, Kagome magnets, and so on. And then we have low temperature STMs. Currently, we have two that go down to millikelvin temperatures with a varying range of autoplane or vector magnetic field. And one of the nice features about this facility is that everything is connected in vacuum using suitcases. So that allows us to study pristine surfaces of materials without ever exposing them to air. So the technique that I use STM, in principle, it's a very simple technique. You have a sharp metallic tip that you bring very close to the sample of interest. So we are talking about 5 angstroms or so. If you apply a bias or a voltage between the sample and the tip, you will get a tunneling current. And you can move the tip across the sample and get essentially STM images. So here on the right, I'm showing some of the most commonly used or acquired data sets. So you can get a simple DIDV spectrum, which is this purple curve, which tells us approximately what is the integrated density of states of the material that we are studying. And probably the most commonly used data set is STM topograph, which is typically acquired the constant current mode. So that means the tip is actually moved across the sample, trying to maintain the constant tunneling current. And what you can see in topograph is both electronic information on the density of states, as well as structural information, such as terraces, defects, and so on. So using this tool, in the past now almost a decade, we studied a wide range of materials. So in yellow here are our homegrown MBE films that we studied using STM. And in white are cleaved bulk single crystals that we get from our collaborators from around the world. So we're interested in topological materials, high temperature superconductors, Kagome metals, and more recently, we've started to dabble into the field of ultramagnets as well, which is the topic of my today's talk. So let me go back to our ultramagnet, cobalt intercalated niobium diselenide, and tell you what kind of experiments and how we are able to do them. So the first thing I want to mention is how do we prepare the sample. So we use the process of UHV cleaving at cryogenic temperatures. So the sample here is this little black line. It has a cleave bar pointing downwards. This is all glued on our sample holder that's above. So schematically, you can think of it this way. This all happens in vacuum. We put a cleaver rod, knocks off the rod, and that creates a pristine surface of the sample in UHV. We immediately insert into the STM head. So if you go back to the crystal structure, these are the niobium diselenide slabs with cobalt intercalated between. The cleavage plane of this system actually occurs somewhere here. So within this intercalated layer, so niobium diselenide slab is actually intact. And that would give you two possible surface terminations in STM data, which is indeed what we see. So the first one here, you can see the selenium surface with a few cobalt atoms left over after the process of cleaving. And if you move around on a different region of the sample or a different sample, we encounter regions that look like this. So there's many different atoms on the surface. We interpret this as the cobalt terminated surface. So most of the talk that I will, or most of the data that I will show today will be focused on the selenium surface. It is quite ordered. So the cobalt surface after the process of cleaving leaves a lot of pits and crevices. So it's actually quite hard to find a complete cobalt surface, but we are able to look at this selenium surface that's stable and flat and clean. And I'll tell you some of the experiments we've done there. So first, let me show you what DIDV spectrum. So if you take a DID spectrum, which again, proportional to the density of states, so y-axis is DIDV, x-axis is STM bias, or could be thought of as the energy in, for example, ARPA's measurement. It shows a notable gap, which at first came a little bit as a surprise. The gap is homogeneous across the sample. So if you take a line cut across this rainbow arrow here, what you can see is the gap of about 30 millielectron volts. So we wanted to see if this is actually due to this antiferromagnetic ordering, so we compare it to DFT calculations. But to our surprise, there was no gap in this system. So right now, as you can see, this is integrated density of states from DFT. There's nothing there. So our just simple experiment that I'm showing here already hints that might be something going on here beyond simple ATOP AFM ordering in the system. Next, we proceeded to look at STM topographs of this selenium surface as a function of STM bias. So in the upper left corner, I'm showing different STM bias that's used. And the second column corresponds to the Fourier transforms. So in addition to seeing selenium lattice, which are these diamonds here, we also see a 2x2 superstructure. So there's additional peaks that you can also see very nicely by eye. Every other selenium atom seems to be brighter than the other. So we want to investigate this in more detail. And what you can see here, we take line cuts from the center of the Fourier transform towards the Bragg peak along the three different lattice directions. So first lattice direction, second, and third. And what we can see is that as a function of bias, which is represented by different colors, this peak at exactly 1/2 Bragg peak location or 2.5 position doesn't shift. So we can put it in a different color scale, but this position is exactly at 1/2 of the Bragg peak length scale. So that tells us there's some kind of 2x2 charge modulations that are static. And importantly, they do not have origin in QPI. So QPI, or quasi-particle interference, is something that we often see in STM images that tells us about the band structure of the material. But these typically disperse as a function of energy. So you will get a different wave vector at different energies, and this is not what we see. What we wanted to explore next is whether these modulations have any spin component. So this system is magnetic, so it's natural to maybe expect this to have spin component as well. And for that, we use spin polarized STM. So I won't introduce the theory of spin polarized STM in depth, but what I just want to highlight at a very high level is that spin polarized STM works by essentially using the same exact conventional microscope, but the only thing that you change is you change the tip wire. So it can still be a non-magnetic wire, but as long as it has a few magnetic atoms at the end with a well-defined spin orientation, you can scan, and the tunneling current will be sensitive to the spins of the sample. So just to explain this, how it works on a real material, so this is STM topograph of iron telluride. It's a bicollinear antiferromagnet. If you take this topograph with a conventional STM tip, you just see these nice tellurium atoms on the surface, but there's no signatures of atomic or magnetic ordering. But then if you pick up a few magnetic atoms and you take the same area of the sample, so you take the same topograph, you can see these three impurities stay the same. You start seeing these stripes. So these stripes are due to antiferromagnetic ordering in play, with spins going up, down, up, down. So let's apply this technique to our sample. So we have a relatively large clean area of the sample, which shows these 2x2 modulations. And then what we do is we use a spin polarized tip, and we are able to control the spin polarization of the tip by external magnetic field. So what we do is we apply a magnetic field along the plus c-axis and then minus c-axis, which flips the spin polarization of the tip and compare the data. So what I'm plotting here on the y-axis is intensity of these 2x2 superstructure peaks. At blue versus red is different orientation of fields. And if there was no dependence on the spin of the sample, one would expect the blue and the red curve to be the same, but you can see that the red and the blue are actually notably different for 1, 2nd, and the 3rd peak. So all 3 peaks show some kind of spin dependence. So intensities are distinctly different. We repeated the same experiment, actually many different samples also on STM topographs. You can see the x-axis here is the magnitude and direction of the field. So negative fields is minus c-axis, positive fields are plus c-axis. You can see that the magnitude of these modulations for 3 superstructure peaks are different or larger for one side versus the other. So there is, in conclusion, some spin component associated with these modulations. But this outcome is not exactly binary, which we found very interesting. So that means even if you look at within one direction of magnetic field, so let's focus on negative fields here. So this is the blue color. You can see that the intensity of these 2x2 modulations actually still increases as you increase the magnitude of the field.
So
Don't count.
sound disappeared.
We didn't.
Okay.
No.
Can you hear me now? Hold on.
This is our side or?
Online is not.
I can hear you
Someone say
guys.
something? Sergey,
Okay.
I can hear
We
you
do not
online.
hear you.
I can hear everyone, so I don't really know.
Перевіримо, він відвалився. Знаєте?
Can you hear me now?
Sergey to say something.
It might be on our side, might be on our side, because I think they're talking.
Yeah, they won't be talking.
I can still hear everything, so I'm
Yeah,
not.
It's on our side.
Now it's fine. Is it okay to continue? Maybe not. Okay.
Say a few words?
Yeah, can you hear me now better, maybe?
Yes.
Yeah, maybe
Okay.
let's switch to another speaker and we will check it afterwards.
Okay, that's okay.
Okay,
Yeah,
good.
as long
So
as
please
everyone
continue.
can hear me, I can continue. Okay. So I'll keep going until I get interrupted again by some technical difficulty. Okay, so going back to our data, we noticed that there is additional intensity variation with the magnitude of magnetic field. So if you look at just the blue color, as you get to a lighter blue, you get higher intensity of these 2x2 peaks. And the only thing that really changes in the intensity of the magnetic field, it's similar for the red color as well. So there is an additional modulation of intensities as the magnetic field increases. So this goes beyond just spin polarized STM and sensitivity due to measurement of the spin polarization of the tip. So this can be explained by samples being tilted by the external magnetic field. Another interesting thing that you will notice in these plots, if you look at the 3 lattice directions, is that the 2nd and the 3rd look pretty similar in their shape, but the first one has these 2 humps. So it almost seems that one direction is different than the other 2. So I wanted to show you that how it looks spatially. So indeed, if you look at the DIDV map, let's say 0 Tesla here, you see this unidirectionality of the modulations. If I take the same area of the sample, so the impurity stays the same at a different field, you actually get something that looks more like 3Q, so similar along different directions. So there does seem to be some tendency of this system to break the rotational symmetry, which is again something that you don't expect from just a simple A-type antiferromagnetic order. Just to conclude this part of the story, I want to show you that there is an additional modulation of the density of states with magnetic field, and we can see that with STM. So the plot I'm showing here is delta DIDV. So it's the DIDV at various fields subtracted by the 0 Tesla DIDV. And you can again see this gradual trend of essentially spectral weight change as a function of magnitude of the magnetic field, and also due to spin tip polarization. So the red curves are just opposite of the blue curves. We performed the same experiment using non-spin polarized tip, just to take that out of the equation. And it seems even with the non-spin polarized tip, you still see electronic band structure change. So red is one field direction is different than the blue. So that means electronic band structure of this material pronouncedly changes as you apply the magnetic field. So what is the origin of these modulations? This is something that we are still trying to understand. So one hypothesis is there are some emergent additional spin and charge density waves. And I'm going to give you some of the reasons why that might be the case. So there is a gap opening at Fermi level that I've shown you at the beginning of talk that cannot be explained by simple A-type antiferromagnetic ordering. So DFT does not capture that. We break rotational symmetry observed by these one-dimensional nature of modulations, which is, again, if you have spins that are purely along the c-axis, they don't pick any in-plane direction. There are two transitions, as I mentioned as well. So the lower temperature transition that people still don't understand what could be the reason, it actually could be due to this additional density waves that emerge. And lastly, I want to mention that pristine niobium selenide, without any intercalation, so it's not an alter magnet, but it does exhibit 2x2 charge density wave if you strain it enough. So the counter argument of these modulations being this additional density wave is, could they be a reflection of the superstructure? So cobalt orders in the 2x2 superstructure, it is well below the niobium selenide slab. So we're measuring the selenium surface. Cobalts are about a nanometer or so below the surface. It's unclear if STM could detect them, but it is conceivable that modulations, at least in part, could be due to some signal coming from well below the surface. However, I do want to mention that we tracked the 2x2 band folding in ARPAS, and if this was purely due to structural ordering of cobalts, we would expect to see it all the way to room temperature, but we only see that to about 100 to 150 Kelvin. So we think there might be something else going on. Okay, so in the last few minutes, I want to tell you about how we can actually visualize domains in ultramagnets using spin polarized STM and the role of single defects. For that, we're using, again, spin polarized STM. I want to highlight how this spatial mapping works one more time. So if you take, going back to our original test sample, which is our telluride, you take identical area of the sample at two different field directions. The two topographies look virtually indistinguishable, but if you subtract them, you get what we call an M-map. You get this stripe pattern, which corresponds to antiferromagnetic order. Okay, so with using different magnetic field directions, you flip the spin polarization of the tip, and you can extract the signal. So let's see what it looks like when we look at our cobalt niobium selenide. So this is a topograph. There's actually a few different impurities that are highlighted here in purple. And if you perform this spin polarized STM experiment to create a spin resolved M-map, you can see that majority of the sample is blue, and then near these impurities, you start getting these red domains. So red is where the conductance is higher, blue is where the conductance is lower. So it seems like there's a nucleation of patches of what we can quote unquote call opposite net spin. We can perform that over larger areas of the sample, over larger energy ranges. It is consistent. So it's, if you focus on the bottom right here, you can see a clear red region with this 2x2 superstructure, and everything else between is blue. And then at a different energy, red flips into blue and blue flips into red. So there's consistent reversal at any energy where it seems that they have opposite trends. So with a tip in one spin orientation, we can extract regions where that are more net spin up and others that are more net spin down. So it does seem that this has a tendency to form these larger scale domains. And I think this kind of tool will be relevant to pretty much other altermagnets as well to characterize domain formation. So in conclusion, I hope I was able to at least convince you that STM and spin polarized STM can be a useful tool to study altermagnets. just due to their underlying magnetic behavior. We provided a rare atomic scale insight into altermagnets. There's actually surprisingly few papers studying these materials using STM. We saw charge and spin modulations that are tunable by external magnetic field, surprising spectral gap opening that cannot be explained by simple A-type antiferromagnet. We think there might be some spin canting in this sample, which could be origin rooted in this rotational symmetry breaking. And finally, we think that there are clearly regions with different kind of response, which I show here in red and blue, which you can think of them as time reversal symmetry breaking domains pinned by impurities. And we think one of the next things to do is to try to identify these impurities to really understand what's going on in this material. I'll leave this acknowledgement slide here for everybody involved in this work, and thank you very much for your time.
Yeah, I was thinking before.
Thank you, Ilya. So now we have a time for questions.
Any questions?
Please.
So, thank you for your talk, Ilya. I had one question about the domain, but I understand probably difficult. Is the domain or the only going down into the system? Is it like still an A stacking or it's just a top layer?
Yeah, it is hard to tell from just simple STM. So STM is a surface probe, and as such, we are probing basically the surface layer. So if you think about if you were probing more than once, let's say probing 2 surface layers, the net polarization would cancel and we wouldn't see anything. So it is just probably just the topmost layer, and we don't really know what's going on below the surface, unfortunately.
Okay, thank you.
So more questions, please?
Oh, please. Okay, I can. Where? Sorry. Okay. So can you hear me? No. Sorry. Okay, can you hear me?
Yes, I can hear.
Okay, good. Thank you. So the question was first. I didn't. You said that cobalt became antiferromagnetic order.
Correct.
And then you show these domains which are ferromagnetic, how it is. But actually, it is a small question. The larger question was the influence of the cobalt on the doping, let's say, on superconductivity. TC it changes, but if it's magnetic, so this question and also that was I was wondering you're using 2H. 2H niobium diselenate. Maybe 1T is more interesting in a sense. They have this is excitonic insulator like a small Fermi surfaces. Okay, that's it. Thank you.
Okay, so let me try. There were 3 questions. So the first one, this is, yeah, it's a layered antiferromagnet, but the top layer is essentially ferromagnetic, and the STM is sensitive to the topmost layer, so that's why we're able to not essentially cancel out this antiferromagnetic order in the way transport would and get 0 net magnetization, but get similarly to what, for example, ARPAs would see, I suppose. And then the second question, cobalt suppressing superconductivity. Yeah, so it's very quickly, you go from niobium to selenide, which is pristine and a superconductor. I forget exactly what cobalt intercalation content, but certainly by the 0.25, which is the sample we are studying, it's not superconducting anymore, unfortunately. And one of the things that would be nice to study, and we have the samples, just we don't have the time, to see how it goes from a superconductor with this 3x3 CDW to this altermagnet that's not superconducting. And we don't really have this phase diagram mapped yet. And the last one, the 2H niobium diselenide, yeah, so pristine niobium diselenide bulk is 2H. You could create maybe monolayer like 1T niobium diselenide. I actually don't know, once you intercalate it with cobalt, is it still 2H? So I don't wanna lie to you, but yeah, different kind of stacking in like 1H, or 1T, 2H, even 4. It would be interesting to look at, but I don't have much to say.
Okay, thank you.
Thank you. Let's thank the speaker again.
Thank you, guys.